Explosions. How do they work? There's a number of ways to implement explosions in your game, each with their own trade-offs and levels of complexity. But today we're going to be checking out a way that I think is really cool, pretty intuitive, and handles a lot of stuff for free. The basic idea is that we want to cast a bunch of rays out from the center of our explosion. Every ray that collides will deal damage to the target it's colliding with that's proportional to how far away the target is from the explosion's center. The tricky part is calculating a nice even spread for all of our rays that's easily configurable. Introducing the Fibonacci sphere. It's just a simple and fast way to fairly evenly spread any number of points over the surface of a sphere. In other words, exactly what we need. I'm not smart enough to explain exactly how it works, but my layman's understanding is that we're basically just mapping a Fibonacci spiral onto a sphere. You can even see that if I start all the way at 0 points and then slowly go up, that there's sort of a spiral emanating out of that point at the bottom of the sphere there. But it's pretty cool. I think it looks awesome. It's very fast. We can even go all the way up to 10,000 points. You can go further, just as far as this slider goes. We will not be using anywhere near that much because it's important to remember that we're not just calculating points. We will be calculating points that we are going to be casting rays to. Rays are fairly computationally intensive. They can lag your game if you have far too many of them that are calculating way too many collisions. You can even see here, these lines you see, they aren't rays. This is just a visualization, but if I crank this number up, you can see it starts to get really laggy, and that's basically what's going to happen with the actual rays that we'll be casting. Luckily, we shouldn't need too many, and you can tune this to whatever you need for your game. But if your game has a lot of explosions going off and you want all of those explosions to be super accurate with lots of rays, then this might not be the best method for you, or you might want to at least look into optimizing this method, because I'm not going to be showing the most optimized form of it, but this should work in 9 out of 10 scenarios. All right, so let's go ahead and get started and see how we can implement this into an example game. For our purposes, I'm just going to be creating a simple time bomb, but you can use this explosion method for any form of explosion, whether that be a rocket from a rocket launcher or a grenade or whatever. But we're going to keep things simple with just a time bomb. So let's go ahead and create a new 3D scene. Let's change the type of our root node here to a rigid body. This is not required. This is just for the purposes of the time bomb itself. This can be any type. But we're going to need a collision shape. And let's make that collision shape into a new sphere shape. And let's also add a mesh instance so we have something to look at. We're going to make this also a sphere, so these things match up. And just for kicks, let's go into the material, create a new spatial material, albedo, color, and let's make that sort of a dark grayish black, sort of get that old-timey cartoon bomb look. This is also going to be a little big, so let's go into the collision shape here and update our radius to 0.3, and we'll need to adjust the mesh instance as well accordingly. So we're just going to go into the radius and say the radius is 0.3 and that the height is 0.6. So that all matches up. Cool. We're going to need one more node. And again, this is not required. This is just for the purposes of the time bomb, but any good time bomb needs a timer. So let's go ahead and add that. Let's rename this to time bomb as well and add our scripts. We can just do default. Go ahead and get rid of all that. We won't need it. And we're going to go ahead and start off by defining a few variables at the top here. We're going to go ahead and get our golden ratio, which is going to be needed for calculating the actual Fibonacci spiral itself. I don't know much about this stuff. If you're interested in the math, I advise looking up stuff about it elsewhere, because I am dumb, but this is what we need, pi times 3 minus the square root of 5. Then we're going to export a few variables that we want to be able to configure, first of which is the base damage per ray. So we're casting a bunch of rays out from the center of our explosion, and as mentioned previously, each of those rays, as they collide with a target, they will deal damage to that target. So this number is going to be the damage that they do. So we're just going to start off with 5, but you can tune this to whatever you want. We also want to be able to adjust the radius of the explosion, so basically how big it is. We're also going to set that to 5. For those of you who may be new to GDScript as well, this little shorthand here, I don't know the actual name of it, but it basically tells the compiler to infer the type of this variable. So we are saying infer the type of radius by whatever value it's being set to. This is the equivalent of saying x bar radius float equals 5.0. It's just a little bit shorter. We're going to be using that a little bit, so it's super helpful. But we're going to do that again with our num points. So this is the total number of points we want to calculate. We're going to start with 250. Again, this is something that you're going to want to tune to whatever your game requires. And then we're also going to want to initialize an empty array of rays. Next, we're going to want to jump into our ready function. And we're just going to call a function that we will write right after this called create rays. That's all we need there. Let's go ahead and define create rays. This is going to return nothing, so we'll say returns void. Then we are going to create a variable called points, and we are going to just assume that we have this function called getPoints that we will define later. GetPoints is where the magic is going to happen, where we're going to actually be doing all the fancy math and stuff. But for actually creating the rays, once we have those points, we want to loop through each point in points, create a new ray stored in a variable called ray. So raycast.new. We're going to want to add that as a child to our time bomb here. And we're going to want to cast that ray to the points that we are looping through. And we are going to be creating these rays as this scene is initialized, right? But we don't need to be running the physics calculations to be checking the collision points for each of these rays all the time. We only care about that when the actual explosion is going off. So that would otherwise be a bunch of unnecessary calculations to run on the CPU and slow our game down. So to get around that, all of these new rays we're going to set enabled to false by default to make sure that they aren't taking up more time on the CPU than they need to be. And just to play it safe, we're going to say we want all of our rays to exclude the parent because we don't want the rays to be colliding with the bomb itself. That would kind of ruin the effect of the explosion. But we will also append each of these rays to our master list of rays that we will access later. But that's everything we need for create rays. So let's go ahead and define our getPoints function and get into the real meat of the Fibonacci sphere. But this is just going to return an array of points. Let's go ahead and define that array at the top here, just an empty array. We'll go ahead and do that as well. And then for point in num points, we need to, I'm not going to be able to explain exactly what's going on here, but I promise you that it works. So if you stick along, follow along, then it should work just fine for you as well. But we're going to start by defining our y coordinate, which is going to be a float, and that is going to be calculated by 1 minus the point we were on divided by our total number of points minus 1 times 2. You may not need all of these extra decimal places. I was having some issues where despite defining this variable as a float, it would still be calculated as just an integer, which will break things. I don't know why that was happening. Maybe it won't be the case for you, but that's why those are there. Next, we're going to define r, which is another float, and this is just going to be equal to the square root of 1 minus y squared, so y times y. And then we need to calculate our angle increment, which I'm assuming is basically the step from one point to another along the surface of the sphere, and that's just going to be equal to our angle times point, the point that we're on. And then we can define x coordinates, which is just cosine of the angle increment. times r. And then z is very similar, except it's the sine of the angle. Increments times r. And lastly, we just need to append this point that we just calculated to our list of points, but we just calculated each of the coordinates individually, so we need to manually construct a new vector 3, which is just x, y, z, and then we need to scale that by the radius we have defined at the top of our script here. These are all calculated as unit vectors, which is why that scaling needs to take place. But it's pretty straightforward. After we've looped through everything, we can finally return our list of points, and we are good to go there. So, oh, there's an extra j up there. That should not be there. We're also going to need a handy little function that we will call getExplosionRayData, which will return an array of all of, we're going to call this function when we are actually exploding, and this function is just going to return all of the rays that we've just created. It's only going to return the ones that are actually colliding, because those are only going to be the ones that we even care about. So for that, let's go ahead and define an empty array here. It's just going to be colliding rays. Give ourselves some room. Then we're going to loop through all the rays we have in our global rays array, and we can go ahead and set them as enabled, because at this point we actually care about whether or not they're colliding, right? This is when the time bomb's actually exploding. Now, the way Godot works, once you set a ray to enabled, it's not actually going to be able to calculate whether or not it's colliding until the next physics frame, I believe. This is all kind of technical, but basically the ray won't be able to check if it's colliding until the next frame, but we want to know if it's colliding on this frame. Luckily, there's a handy little function for that, which is just ray force raycast updates. So that will handle that for us, which is super handy. Then we can just check if our ray is actually colliding. And if it is, then we want to append it to our colliding rays array. And then we just return that. Oops, there we go. And that should be all we need for getExplosionRayData. What's going on here? Oh, looks like I'm missing an eye. Perfect. Now let's actually go ahead and define our explode function. So this is what we want to call when the timer is up. For that, we need to get the rays that we that are actually colliding. So we can do that using the function we just defined. And then we can loop through each of those in explosion rays, and we can define a variable where we can store the actual object that each ray is colliding with. So that's how we do that. And so there's a number of ways you can do this next part, which is actually telling whatever object the ray is colliding with that it's taking damage. What I'm doing, the way I'm doing this is I'm assuming every object that can take damage has a function called take damage. And it's in this function that will handle, of course, taking the damage, whether that be reducing a health pool or playing some sort of explosion or break apart effect. But regardless, we're assuming that they have this take damage function. There are other ways to do this, but this is the way that I chose. So for that, we just need to check if our collider has that method, which is just take damage. And then we need to actually calculate the damage. And let's just put that in a function that we will write later. And for that, we'll just need to pass in the collision points of the ray, because, of course, as we talked about before, the way we're calculating damage is just the distance from the center of the explosion, which is we're going to need the collision point of the ray to actually calculate. And then now that we know it has this method and that we've calculated the damage it's supposed to take, we'll just call that method and pass in the damage that we just calculated. Now, Oh, one last thing, of course. We just exploded, so we should probably get rid of this thing that just exploded. So we'll call queue_free to get rid of our time bomb. And that's all we need there. Now, I should mention, we're going to go ahead and define this calculate damage function. And we'll go through that whole process, but this is actually optional, right? So one of the advantages we get with this method for handling explosions is that the further away an object is from the explosion, it will naturally end up taking less damage, right? Because less rays will actually be colliding with it. So you don't necessarily need to reduce the damage of each individual ray based on the distance the object is from the explosion, because they'll already be taking less damage anyway. But in case you want to include that as well, we're going to go ahead and use this calculate damage function. But if you don't want to do this, instead of saying writing this whole function for calculating the damage, you can actually just get rid of this and return, what was it called? Base damage ray? Why did we name it that? That is a bad name. It should be base damage per ray. That makes a lot more sense. So yeah, instead of doing some fancy, well, it's not that fancy, but doing some math to calculate the damage, you can just pass in this fixed value, and you'll still get the effect of reduced damage taken the further away an object is from the explosion. But let's continue on with what we were doing originally, and instead use this calculate damage function to get the damage, and pass that in to the take damage function. So in calculate damage here, we are of course passing our collision point, which is passed as a vector 3, and then this function itself will just return a float. That is, of course, the damage. The first thing we need to do, though, is calculate the distance from the explosion, and for that, it's just a simple matter of taking the global translation of the explosion itself and calculating the distance to the collision point that we have, passed into our function here. If I can type. There we go. That's a little bit better. And then we want to calculate the damage itself based on that distance, and that's going to be as simple as getting our base damage per ray and multiplying that by the radius minus the distance divided by the radius. So all that we're doing here is we are calculating a value between 0 and 1 and multiplying that by the base damage per ray. So if the object that is taking damage is right on top of the explosion, then the distance will basically be 0, and then radius minus that is going to be basically equal to radius. Radius divided by radius is equal to 1, so we'll get the full base damage. If they're any further, though, then this value will be reduced, which means this value will be reduced as a whole, which means this value will be reduced as a whole, and we'll end up taking less damage. Last thing we want to do, of course, is return that damage. However, we want to put in a nice little safeguard here. So the way we're calculating our points, there should never be a scenario where a ray is colliding when the object that's taking damage is actually further from the explosion than the defined radius, because the rays should only be casting out exactly to the radius. However, just to play it safe, what we can do is we can say return damage if damage is greater than 0, else 0. So if for some reason we did end up registering that a ray was colliding, even though someone was further from the explosion than the radius itself, then this value as a whole might end up becoming positive, negative. And we don't want to return a negative damage, right? Because if our take damage function assumes that we want to do health pool minus damage, then that will end up actually healing the target, which would be kind of weird. So we're just saying if damage is greater than 0, then yes, go ahead and return it. Otherwise, let's just assume it did no damage at all. That's all that's happening there. But that is basically all we need. The last thing to do is just to call our explosion, and for that we need to actually go to our timer and let's increase the wait time to like 5 seconds and say it's one shot. This isn't actually really necessary because we'll be deleting this whole node as soon as it explodes, but might as well do it. And then we want to auto start as well. And let's go into our signals and connect timeout to our script. And in this timeout function, let's get rid of that extra space. We just want to call explode. And that should be all there is to it. But of course we have to actually integrate this into the rest of our game, and that's just going to depend on your particular implementation. If you are already aware of how to do that, you can just stop the video here and go ahead and get started. But for those of you who want to see this in action and maybe don't have something set up, I'm going to go ahead and also go through a simple scene setup where we can just demo everything we just wrote. So let's go ahead and just create a new scene. This is going to be real quick and dirty. Well, let's go to 3D view just so we can see more of what's happening. We'll just do a new 3D scene. And let's go ahead and add a CSG combiner. And as a child to that, we'll add a CSG box. And this is just to create a quick and dirty floor. So let's just make it nice and flat and big so we have something to walk around on. Okay, cool. And then if you go to the assets library, I believe, what is it? First person, simple first person controller. There's this nice little add-on someone already made that's all prepared for us, and you can just download that, install. Okay, and that adds this handy little scene for us that we can instance as a child scene to our main scene. And so now we've got this player object here, and all we need to do is jump into the script of the player, go down to handle input. Oh, it looks like I actually already have this script modified. Yeah, I do. This is basically what we're going to be writing, but let me just go through all that for you. First thing you're going to want to do once you've added this is go into your project settings, go to input map, and we're going to need to add all of these. So if you scroll to the top of this file here, this person was kind enough to put all of the action strings at the top, and all you need to do is write the string that that action is set to. So like for instance, we've got player forwards. I already have that added, but you just click add and then scroll down to the bottom where it'll be like right here. And then you can click on the plus icon, do physical key and set that to whatever you want. Probably gonna be W. I already have that set though, so we'll just cancel. You're gonna wanna do that for, you don't have to do all of the actions. You might get some errors spit out in the console, but you can add all of them if you want. The important thing though is we want to add a custom one, which is not here, which is just going to be shoot. I've already added that as well, but it's not there by default. And you're just going to want to set that to mouse button and device 0 left button. And once you've got that set up, you can close and you can scroll to the bottom of handle input, and we can just say if input dot is action pressed, or let's do is action just pressed, and we want to do shoot. And all we need to do is make sure that we have a preloaded version of our bomb scene. So just add this variable at the top, bomb scene preload, and you can just drag and drop the the scene we just created, just like that. So then we've got our bomb scene, and then down here we want to instance that. So we can say bomb scene dot instance, and then we want to add that as a child to the scene. We need to control where it is though. So I've actually gone in, and in the player scene, you can add a quick position 3D. And so here's our new position, and you can just move that up and sort of put it in front of the camera. And then in the player script here, we can say bomb.global translation equals $ position 3D global translation. Oh, and this should not just be at child. What we want to do is say get parent.addChild, because we don't want to add the bomb as a child to the player. We want to add it as a child to our main scene, so it's not connected to our player in any way. But then we should be good to go. Let's see what happens if I save, and here's our scene. If I save this, we'll just call it main, and then we run this scene. Let's see. Oh, we fell through the floor. I almost forgot. In CSG Combiner, you want to use collision. So that doesn't happen. We'll just select current. There we go. So we can walk around. It's really, really ugly because everything's really stark white, but it is working. And if I click, it looks like it spawned behind me for some reason, but sure enough, we've got a time bomb. And after 5 seconds, it deletes itself. And let's just spawn like a bunch of those. So that's working. We also need to do is we need to make sure we have this take damage function, right? That the time bomb is actually looking for. So if we go back to our player scene, go into our player script, you can just add a function at the bottom called take damage, takes in our damage value, and then do whatever you want with that damage. For our purposes, I'm just printing it out so that we can make sure everything looks good. But you're probably going to want to do something like health minus equals damage or something like that. But we can use this to test things. So let's go ahead and start the scene again, drop our bomb, stand right next to it, and have it go off. And sure enough, look at that. We've got a bunch of damage values from all the rays that were colliding with us. And now let's also verify that if we spawn a bomb, go a little bit further away, we should have less of those rays. Looks like we were a little too far away. Let's try that. And let me clear this as well. Let's see. Whoops. So after some debugging, a small error on my part to fix in the time bomb script that we created when we are actually calculating the points when we were actually constructing the point, I was multiplying by just r, this r variable here, but we want to multiply by the radius defined at the top. Sorry about that. Just add radius here, and that should fix things. For instance, if we play the scene now and spawn a bomb, and I can be a little bit further away, it explodes. Sure enough, we only get hit by 3 rays, but they're each doing their own amount of damage. We can just add a whole bunch of them, watch them all go off. All do different amounts of damage. We've got some less than 3s, as expected. Yeah, everything seems to be working. Of course, visually, there's not a lot happening right here. You can do a lot more to do that. You can add some particle effects, make the explosion look nice. This is more just a functional tutorial. But hopefully this was helpful. Hopefully you found it fun and something that's useful for your project. I hope you have fun integrating it. And if you have any issues, feel free to put them in the comments, and either I or maybe someone else who's watching this video can try and help out. But best of luck. Let me know what you think.